The topic of this lecture is segmentation. There is a problem with the base and bound approach. Even though there are a big chunk of free space in the virtual address space, as you can see here, the free space also takes up the physical memory. There are 16 kilobytes of virtual address space. Program code occupies 2 kilobytes. Heap occupies 2 kilobytes. And also stack occupies 2 kilobytes. Out of 16 kilobytes of virtual address space, 10 kilobytes is free. However, because all virtual address space are allocated as an entire single unit, the address space for free address spaces also occupies the free address space. So this is a big problem of base and bound approach. So it's hard to run when there is no address space that can accommodate the entire virtual address space. The program cannot fit into physical memory. Let me explain the notion of segment. Segment is contiguous portion of address space of arbitrary length. So code and stack and heap, all of them forms a different segment. And in segmentation-based relocation approach, each segment can be placed at different parts of physical memory. So it's very similar to the concept where the base and bounds exist per each segment. So if the hardware allows 3 different segments, such as code, stack, and heap, then hardware should provide 3 pairs of base and bound register. This is an example of placing segments in physical memory. A program consists of 3 segments: code segment, heap segment, and stack segment. And the size of each segment is 2 kilobytes. Operating system has loaded each segment at different address region. The code segment was loaded on the base of 32 kilobyte. The heap segment has been loaded onto base address of 34 kilobyte, and stack segment has been loaded to the address of 28 kilobytes. So this is physical memory. From 0 to 16 kilobytes, operating system was loaded, and from 16 to 64, entire memory region was freely available, and the operating system has placed these 3 segments in different address region. Remember that in code segment, the size does not change. Heap segment grows downward, and stack segment grows upward. So when operating system allocates these 3 segments, it has to pay attention to where it places. Let's explain how we translate the address. Let's start from the code. The physical address of a code is offset plus the value of the base register. Let's consider an instruction which is located at the 100. And then, because the code are placed at the virtual address space 0, so the physical address of this instruction is 100 offset plus the value of the base register 32K. So as a result, the physical address of a given instruction is 32868. This is the desired physical address. Second thing is the address translation on the heap. According to our segment allocation table, the base address of the base is 32K and the size is 2 kilobytes. And we are trying to load the data starting from 4200. The address of the heap starts at 4 kilobyte, which is 4096. So the address of data is 4200. So difference between the two is 104. So the physical address of a given object in the heap corresponds to 104 plus the base of the heap, 32. So the desired physical address corresponds to 34920. If an application tries to access the address such as 7 kilobyte, then this region has not been allocated for any of the segment in the virtual address space. The operating system generates segmentation fault. Of course, the hardware detects the address that it is an illegal address, and then once hardware raises exception, then operating system executes associated exception handler and then prints out the message segmentation fault. The next issue is how can we identify which segment the address space belongs to. There is an explicit approach. An explicit approach chop up the address space into segments based upon the top few bits of the virtual address. It uses leftmost some bits as a segment identifier. There is 14 bits in total in this hardware architecture, and it allocates leftmost 2 bits as a segment identifier. For example, for segment code segment uses 00, heap segment uses 01, stack segment uses 10, and because there are only 3 types of segment, bit 11 is not used. To save more address space, because code and heap can be coalesced together, then in this system, they can allocate code plus heap as a single one segment, and then stack as another segment. Then they need 2 bits. Then they can use only 1 bit for segment identifier, and then use 13 bits for an offset. Let me explain how we select segment through the software code. First, segmask is extracts leftmost 2 bits out of 14 bits, and segment shift is 12 bits, and then offset mask is all ones except the leftmost 2 bits are 0. So first, in the line 2, it extracts the segment ID, the leftmost 2 bits, and then in line 4, it extracts the offset, and then check if the offset exceeds the bound. If everything's okay, then from the base bound table, it gets the base address and adds it to the offset, and then it gets the address, and then gets the contents from the memory to the register. One thing you want to know about is in this code, the base and bound address pairs are stored in the array. Base and bound are stored in the array, and the index is segment. Stack is slightly different from the code and the heap because stack grows backward. So segmentation scheme has to allocate extra bits to specify whether a given segment grows forward or grows backward. So 0 means positive direction and 0 means negative direction. So for each segment, code, heap, and stack, the segment register has to specify base address and size and the direction of the grow. Using segment, the processes can share a segment easily. Segment can be shared between the address space. Code sharing is still in use in the systems today. Let's consider a server, and there are tens of users logged into the server, and they all are editing some sort of program using an editor Vim. In normal situation, each process that edits the code will contain the code for VIM, and if there are tens of users in the system, then there's going to be tens of copies of Vim loaded on the memory. But if the operating system allows the sharing of the code segment, then all the users can share the same copies of the code. So instead of loading tens of copies of Vim, operating system creates a single copy of Vim code, Vim text, and then allows it to be shared among the different users. But in that case, we need extra hardware support. Extra hardware support is needed for the protection. So we can also allocate a few more bits per segment to indicate the permission of read, write, and execute. So in total, to realize segment, we need base register. Not register, but so far we haven't specified whether we're going to use register or we're going to use a simple table in supporting segment. Anyway, in this case, we have, for each segment, we need a base address, and the size, and the direction of growth, and the protection. So these are the amount of information the hardware has to provide to support segment. The segment can be fine-grained or coarse-grained. In coarse-grained segment, there are a very small number of segments. For example, there are code, heap, or stack. Fine-grained segment allows more flexibility for address space in serverless systems, but there has to be there can be a large number of segments, like thousands or 2,000 or something. So we cannot allocate 1,000 pairs of registers for each segment. In that case, hardware has to support segment table instead of base pair register for each segment. The problem with segmentation is external fragmentation. As you allocate and deallocate segmentations a number of times, there can be lots of little holes of free space in physical memory that is too small for allocating any segments. Let's consider the following scenario. There exists total of 24 kilobytes of free space in the physical memory, but they are not in one contiguous segment. And then operating system needs to allocate 20 kilobytes request. In that case, even though there are 24 kilobytes of free space in total, operating system cannot accommodate 20 kilobytes of segment into the free physical memory. The only approach to address this problem is compaction. Compaction is an activity of rearranging the existing segments into physical memory. Compaction is costly. Let's say there are three segments, here, here, and here. And then in compaction, it moves the existing segment into one direction and makes the big free chunk, like this. So that this is free, and this is free, and this size is S1, and this size is S2. And then after compaction, it creates free segments of size of S1 plus S2. But compaction is costly, and it is barely used. Well, to be honest, it's not used at all. It has to stop all the existing running process, and it copies the data to somewhere, and then it changes segment register value for our processes. So that's very costly. This is what memory compaction looks like. There is an operating system, and this part is allocated, and allocated. And as a result of compaction, it migrates this space to this part, and this part. And then it creates a free big chunk of physical memory region. So that is what the compaction is for. Segmentation has long history. In early days, computer system relies on segmentation to implement virtual memory. Burroughs B5000, IBM AS400, and the recent Intel architecture 8086 and 8286. Starting from 386 and later, Intel starts to support paging. These days, 64 process 86 architecture does not use segmentation anymore. It sets the CS, SS, DS, and ES value as 0. Now these are all the base register for the 4 segments. In summary, segmentation can better support sparse address space than branch and bound register approach. branch and bound register approach. And it is also fast as the overheads of translation is minimal. And sharing is easy, but it has two issues. First one is the external fragmentation. And second one is sparse segment. The sparse segment, consider a heap segment. This is heap segment. The heap segment, somehow only the beginning of the segment and the end of the segment are being used, and in the middle are all free. In that case, segmentation has to allocate the physical memory on segment granularity. So this part is still allocated even though it is not used. That is the problem of segment.